Let's look at Taylor-Maclaurin polynomials. You remember when I have a general function that the first order linear approximation, P1, is some A1 plus, or A sub naught, plus A1x. So this is just a line. A second order approximation is A naught plus A1x plus A2x squared. The third order approximation gets much closer, and that's P3 is A naught plus A1x plus A2x squared plus A3x cubed. But finding these terms, the A1s, the A2s, the A3s, can be a bit of a challenge. Now, it's obvious that we want to go into higher order polynomial approximations to get much closer to our functional value near our point. Now, Taylor and Maclaurin expansion or polynomials help us out quite a bit here. Suppose I have a function f that has n derivatives. Then the polynomial p sub n is fc plus f prime at c times x minus c plus f of double prime at c divided by 2 factorial times x minus c squared plus on and on. The nth derivative evaluated at c divided by n factorial times x minus c to the n is our nth degree Taylor polynomial. Now, sometimes we expand about c equals 0, and this has a special name, and this is Maclaurin polynomial. And all we're doing is replacing the c with 0. Well, let's try one of these. Let's look for the nth degree Maclaurin polynomial for f of x is e to the x. So Maclaurin tells me c is 0, so I'm going to be expanding about x equals 0. So f of x is e to the x, f prime of x is e to the x, f double prime of x is e to the x. Okay, you kind of see where this is going. I'm not going to care. Let me do f triple because I want to show you the triple. But let's keep going. The nth derivative of x is just e to the x. So let me evaluate these at c equals 0. F of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1, f triple prime of 0 is 1, all the way down, third there, yeah. The nth derivative of 0 is just 1. So now I want to write the actual formula for the Maclaurin expansion. P sub n of x is equal to f evaluated at 0 plus f prime evaluated at 0 times x. Now I'm going to put this on here, divide by 1 factorial, plus, because 1 factorial is just 1, plus f double prime evaluated at 0 times x squared divided by 2 factorial, plus f triple evaluated at 0, x cubed divided by 3 factorial, plus, and then my nth term is the nth derivative evaluated as 0, x to the n, divided by n factorial. By writing it this way, we'll see our patterns. So Pn of x for this function is 1 plus 1x over 1 factorial plus 1x squared over 2 factorial plus 1x cubed over 3 factorial plus 1x to the n over n factorial. Now I know that's hard to read, so I'm going to rewrite it. So this becomes 1 plus x squared over 2 factorial. Usually we start throwing in the factorials after we get to 2 factorial. X cubed over 3 factorial plus x to the n divided by n factorial. Now suppose we want to find the Taylor polynomial for a log of x centered at c equal 1. You do the same thing. You need to find the first, in this case, 4 derivatives. So f of x is the natural log of x. F prime of x is 1 over x. F double prime of x is minus 1 over x squared. F triple prime of x is Now it's minus a minus 2 over x cubed. So this is going to be plus. Now I'm going to write it this way for a reason. It's plus 2 factorial, and you'll see why I'm writing it this way in just a second. Now the fourth derivative is minus, so you see this is going to be 3 factorial divided by x to the fourth. We're going to use this when we expand this just a little bit more. So next we need to come in and find what is our functional value at each of these points. So f of 1 is the natural log of 1 or 0. F prime of 1 is just 1. F double prime of 1 is minus 1 over 1 squared, so it's negative 1. F triple prime at 1 is 2 factorial divided by 1 cubed, or in this case just 2. And f to the fourth of 1 is minus 3 factorial divided by 1 to the fourth, and I'm just going to write this as negative 6. So what are the Taylor polynomials? P sub 0 is just the 0th term, so it's just the first term, so it's just f evaluated at 1 or 0. P sub 1 of x is f evaluated at 1 plus f prime evaluated at x minus 1. So this is going to be f of 1, which is 0, f prime at 1, which is 1, times x minus 1. So this is just x minus 1. P2 of x, second order approximation, is f of 1 plus f prime at 1 times x minus 1 plus f double prime at 1 divided by 2 factorial times x minus 1 squared. So when I plug this in, that term's still 0. This term is x minus 1. Now, what is this term right here? F double prime at 1 is negative 1 over 2 factorial times x minus 1 squared. So how are we going to write this? For P2, just write it as x minus 1 and put that parentheses there, minus 1/2 x minus 1 squared, and just leave it. Now let's look at P3. P3 of x is f of 1 plus f prime evaluated at 1 times x minus 1 plus f double prime at 1 divided by 2 factorial times x minus 1 squared. Now I need my third term. So it's f triple prime at 1 times x minus 1 cubed, I'm running out of room, divided by 3 factorial. When I plug in my values, that's still 0. You see how we're basically adding on to our previous expansion. So this is going to be plus 1 over 3 x minus 1 cubed. Now for the fourth one, P sub 4, and I'm going to go in and do this. This is painful, I know. This is f evaluated at 1 plus f prime evaluated at 1 times x minus 1 plus f double prime at 1 divided by 2 factorial times x minus 1 squared plus, I need some space here, f triple prime evaluated at 1 times x minus 1 cubed divided by 3 factorial, and then my fourth term is the fourth derivative evaluated at 1 divided by 4 factorial times x minus 1 to the fourth. And remember, my fourth derivative is negative 6. So when I plug in my values, this becomes x minus 1, this is my first order, minus 1/2 x minus 1 squared, there's my second order, plus 1/3 x minus 1 cubed, here's my third order, and then my final term becomes minus 1/4 x minus 1 to the fourth. So this is my fourth order approximation.